40.1 trillion kilometers. That is the distance to the nearest star, not the nearest galaxy, not the nearest cluster, the nearest single star, one star, 4.24 light years. And the fastest thing humanity has ever launched into space would need 73,000 years to cover that distance. Let that settle for a moment. 73,000 years ago, modern humans had not yet painted the caves at Lascaux. We had not yet crossed into the Americas. Writing did not exist. Mathematics did not exist. Cities did not exist. And a spacecraft launched today at maximum achieved human velocity would still be traveling, still in the dark, still in the void between stars, when civilizations we cannot imagine rise and fall thousands of times over. Proxima Centauri is not unreachable because we lack ambition. It is unreachable because the laws of physics make a specific, testable, mathematical argument for why nothing with mass can ever cross that kind of distance in any time that matters. And we are going to work through that argument completely and honestly right now. If you love deep space deep dives, you can subscribe. It helps more than you think. Proxima Centauri is 4.24 light years away. That phrase, light years, is one of those expressions we use so casually that it has lost almost all meaning. We say it the way we say $1 million, as shorthand for something large. But a light year is not an abstraction. It is a precise physical distance. The distance light travels through vacuum in one full year, moving at 299,792 kilometers per second. 1 light year is approximately 9.46 trillion kilometers. Say that number slowly. 9.46 trillion. Now multiplied by 424, the distance to Proxima Centauri is roughly 41 trillion kilometers. 41 million kilometers. If you lined up every single human being who has ever lived, an estimated 108 billion people, shoulder to shoulder in a chain, you would not even begin to make a dent in that distance. The chain of every human who has ever drawn breath would stretch perhaps 170 million kilometers, less than 0.5% of the way to Proxima Centauri, not even past the orbit of Mars. Let us try another approach to the scale. The diameter of Earth is roughly 12,742 kilometers. The distance from Earth to the Moon is about 384,400 kilometers, roughly 30 Earth diameters. That is a distance we have traveled. We sent human beings there in 1969, and it took about 3 days. The distance from Earth to the Sun is about 150 million kilometers, nearly 400 times the Earth-Moon distance. The distance to Proxima Centauri is 40.1 trillion kilometers, roughly 270,000 times the Earth-Sun distance. To put it differently, if the Earth-Sun distance were 1 centimeter on a map, Proxima Centauri would be 2.7 kilometers away, and that is the very nearest star. Most stars in our galaxy are hundreds or thousands of times farther than that. The galaxy itself, from one side of its disk to the other, would be 100,000 kilometers away on that same map. To make this real in terms of what we have actually built and launched, consider what we have actually sent into space. Voyager 1 is humanity's most distant object. Launched in 1977, it has been traveling through space for nearly 5 decades, and it has covered an astonishing distance, currently sitting at around 23 billion kilometers from the Sun. That sounds enormous, but it represents less than 0.06% of the distance to Proxima Centauri. At Voyager's current speed of approximately 17 kilometers per second, it would take roughly 73,000 years to reach our nearest star, if it were even pointed in the right direction, which it isn't. 73,000 years. That is longer than modern anatomically human beings have been writing, painting, building, or recording anything at all about their existence. It is nearly as long as our species has existed with fully modern cognitive capabilities. The Parker Solar Probe, our fastest spacecraft, has reached peak speeds of around 163 kilometers per second during its closest solar flybys, velocities achieved by diving deep into the Sun's gravity well and using that gravitational energy to accelerate. That is the fastest a human-made object has ever moved, and it is genuinely staggering from an engineering standpoint. But at that speed, reaching Proxima Centauri would still take approximately 700-800 years. New Horizons, which gave us our first close-up images of Pluto and continues traveling into the outer solar system, travels at about 14.5 kilometers per second and would need roughly 87,000 years. Every probe we have ever launched, every satellite, every capsule, every piece of hardware we have ever thrown into space, with every gram of thrust we could muster. All of it would take thousands upon thousands of years to reach even the very first star beyond our own. Here is another way to feel the distance. The light that left Proxima Centauri tonight and is streaming toward us right now. That light began its journey 4.24 years ago. The star you are looking at when you look at Proxima Centauri is the star as it was in the early days of whatever you were doing 4 years ago. And that light, which travels faster than anything in the universe, faster than any particle with mass can ever travel, still needed 4 years and 3 months to get here. The universe operates on timescales and distances that our nervous systems never evolved to intuitively grasp. Everything our ancestors needed to survive, finding food, avoiding predators, navigating terrain, happened on scales of meters to hundreds of kilometers. Our intuitions are calibrated for a world roughly 1,000,000 times smaller than the distance to the nearest star. We are not equipped to feel how far away it is. We can only calculate it. This is not a problem we can engineer our way around by making a faster rocket. The distances involved are not merely large. They are large in a way that exposes fundamental physical constraints. And to understand why, we need to talk about the speed of light and about what Einstein understood about it that changed our picture of the universe forever. Light moves at 299,792 kilometers per second. In the time it takes you to blink, roughly 150 milliseconds, light travels from Earth past the Moon and continues on. In a single second, it travels a distance that would take our fastest spacecraft several hours. In 8 minutes, it crosses the entire distance between Earth and the Sun. In 4.24 years, it reaches Proxima Centauri. And here is the thing about light speed that took the greatest minds in physics over 2 centuries to fully work out. It is not just a speed that happens to be very fast. It is a fundamental constant of the universe, a hard ceiling built into the structure of space-time itself. Nothing with mass can reach it. Not technically reach it slowly, not gradually approach it over a long enough time. The laws of physics do not permit it, and the reason why is both beautiful and deeply frustrating. This was Einstein's discovery, formalized in his 1905 paper on special relativity. The core insight is this: the laws of physics are the same for all observers moving at constant velocity, and the speed of light is the same for all such observers regardless of how fast they themselves are moving. That second part is the strange part. If you are traveling in a spaceship at half the speed of light and you shine a flashlight forward, you might expect the light to travel at 1.5 times the speed of light relative to a stationary observer. But it doesn't. That observer also measures the light moving at exactly the speed of light. This is not a paradox. It is a feature of how space and time themselves are structured. Space contracts in the direction of motion, and time dilates, slows down, for the moving observer. These are not illusions. They are not approximations. They are real, measurable, experimentally confirmed consequences of the universe we actually inhabit. The Michelson-Morley experiment in 1887 was one of the first signs that something was deeply wrong with the classical picture. Scientists expected to measure variations in the speed of light depending on the direction they measured it, because if light traveled through a medium called luminiferous ether, and Earth was moving through that ether, the speed of light should vary depending on whether you were measuring with or against the Earth's motion through it. They found no variation at all, 0. Light moved at the same speed regardless of the direction of measurement, regardless of Earth's velocity, regardless of anything. That result baffled the physics community for nearly 2 decades. Einstein resolved it by simply accepting the implication the speed of light is the same for everyone, always, and space and time must bend and flex to make that possible. As an object with mass accelerates toward the speed of light, something happens to it. Its relativistic mass increases. This is not a metaphor or an analogy. It is a measurable physical effect. The faster something moves, the more energy it takes to accelerate it further, and the more resistant it becomes to further acceleration. When you are at 10% the speed of light, your relativistic mass is nearly the same as your rest mass, and things still feel relatively normal from a Newtonian perspective. At 50% the speed of light, your relativistic mass is roughly 1.15 times your rest mass. Noticeable in principle, but not extreme. At 90% the speed of light, your relativistic mass is about 2.3 times your rest mass. At 99%, It is more than 7 times your rest mass, and 99.9% it is over 22 times. And 99.99% it is over 700 times your original rest mass. The closer you get to the speed of light, the more your mass effectively increases, and therefore the more force it takes to push you even a fraction of a percent faster. The energy required to close that final gap, to go from 99.99999% the speed of light to 100%, is literally infinite. The universe enforces this with perfect impartiality. No engine, no matter how powerful, can overcome it, because the obstacle is not an engineering challenge. It is a mathematical one, written into the equations that describe space-time itself. Now, there is one concept from relativity that might seem to offer a loophole, and it deserves careful treatment rather than a quick dismissal. Time dilation. As you travel at velocities approaching the speed of light, time inside your reference frame slows relative to time experienced by stationary observers. A traveler aboard a ship moving at 99.9% the speed of light experiences only 1 year of subjective time for every 22.4 years that pass in the external universe. At 99.999% the speed of light, that ratio becomes far more dramatic. A traveler might age only months while years pass outside. In principle, a traveler could cross tens or hundreds of light years of physical space while aging only a small number of years. The physics here is not speculation. Time dilation has been measured with atomic clocks flown on aircraft and satellites. GPS systems require relativistic time corrections to function accurately. Muons produced in the upper atmosphere by cosmic rays survive long enough to reach Earth's surface only because their internal clocks run slow relative to ours, a consequence of their extreme velocities. Time dilation is as real as gravity, but here is why it does not solve the problem, and why understanding the distinction matters. Time dilation is entirely directional from the perspective of a civilization. The travelers aboard the ship might experience only 5 years of subjective travel to a nearby star, but back on Earth, decades have passed. If you wanted to send a crew to a star 10 light years away and have them return, centuries would have elapsed on Earth by the time of their return. Regardless of what they experienced on the ship, the society that launched them would be gone. The institutions, the governments, the individuals who sent them, all history. The children of those who saw the launch would themselves be long dead. More fundamentally, even if you accept that trade off for the travelers, you have gained nothing in terms of information speed or civilization connectivity. A message sent from the destination still takes years to arrive. A colony planted at a distant star is functionally disconnected from Earth from the moment it is established. Not just practically disconnected, but physically so, in a way that light, speed communication cannot repair. You could have a real-time conversation with someone on Mars with only a few minutes of delay. You could exchange messages with someone in the asteroid belt with hours of delay, but from Proxima Centauri, every message takes 4.24 years each way. A question and its reply take over 8 years. Genuine back and forth communication, the kind that allows a civilization to function as a coherent entity, is simply impossible across interstellar distances. Time dilation compresses the experience of the journey for the travelers. It does not shrink the universe. There is also a deeper philosophical problem with time dilation as a practical tool. To exploit it meaningfully, to make the journey in, say, subjective months rather than years, you need to travel at an extraordinarily high fraction of the speed of light. And as we have discussed, accelerating to those speeds requires energy that scales catastrophically. The benefit of time dilation grows as you approach the speed of light, but so does the energy cost, and the two curves do not balance in any way that makes the scenario achievable with foreseeable technology. You cannot get the time dilation without first solving the energy problem, which is, as we will discuss shortly, its own kind of impossibility. Before leaving the realm of the speed barrier entirely, let us be direct about the two ideas that most people's minds immediately jump to when they hear about interstellar travel wormholes and warp drives. Both appear in the mathematics of general relativity, at least as theoretical objects, and both are frequently cited in popular science coverage as potential solutions. The enthusiasm is understandable. The math does generate these solutions. But what the popular coverage almost always omits is the physical price tag attached to each of them. A wormhole in general relativity is a hypothetical topological bridge connecting two separated regions of spacetime. The concept was first explored seriously by Einstein and Nathan Rosen in 1935, the so-called Einstein-Rosen bridge. In their original formulation, it was not traversable. Anything that entered one end would be destroyed before reaching the other. Later work by Kip Thorne and colleagues in the 1980s showed that a traversable wormhole is at least mathematically consistent with general relativity, but it requires something called exotic matter, matter with negative energy density, not dark energy, not antimatter, but a specific form of matter that has negative mass, matter that, rather than attracting other matter gravitationally, repels it. There is no observational evidence that such matter exists anywhere in the universe. There is no established theoretical mechanism by which it could be produced. The Casimir effect, a quantum phenomenon in which two uncharged parallel metal plates experience a very slight attractive force due to quantum vacuum fluctuations, has been proposed as a source of negative energy, but the energy densities involved are infinitesimally small compared to what would be needed to stabilize a traversable wormhole large enough for a spacecraft. The gap between what the Casimir effect produces and what a usable wormhole would require is so vast that comparing them is almost meaningless. A traversable wormhole is not merely undiscovered engineering. It requires the existence of a class of matter that may simply not exist in our universe. Warp drives face similar problems, but with even less theoretical ground to stand on. The Alcubierre metric, proposed by physicist Miguel Alcubierre in 1994, describes a mathematical solution to Einstein's field equations in which a bubble of flat spacetime surrounds a spacecraft while the space in front of it contracts and the space behind it expands. The ship within the bubble is locally stationary. It does not move through space, and therefore does not violate the special relativistic prohibition on faster than light travel through space. Instead, the bubble of space itself moves, carrying the ship with it, faster than light. The mathematics, within the equations of general relativity, is internally consistent, but the physical requirements are staggering. Alcubierre's original formulation required exotic matter with negative energy on the order of the mass, energy of Jupiter, arranged in a precise geometric shell around the spacecraft. Later refinements have reduced the theoretical requirement, but exotic matter is still needed, and the fundamental instabilities of the warp bubble geometry, the fact that nothing inside the bubble can influence the bubble wall without itself violating causality, present problems that remain unresolved. A warp drive is not an engineering challenge awaiting better materials. It is a theoretical artifact that assumes the existence of physics we have no evidence for, in configurations we have no mechanism to create, operating in ways that may violate causality itself. It belongs in the category of mathematically legal but almost certainly physically forbidden. Let us turn to energy. Because even if we set aside the absolute speed limit and ask merely what it would take to get a spacecraft to a meaningful fraction of the speed of light, the numbers are sufficient to induce a kind of quiet vertigo. The relativistic kinetic energy of an object moving at velocity v is given by the Lorentz factor times the rest mass energy minus the rest mass energy, a formula that, at low speeds, reduces to the familiar TMVI, but at high speeds diverges dramatically from Newtonian expectations. To accelerate 1 kilogram of mass to 10% the speed of light requires roughly 450 trillion joules, about 450 terajoules. The atomic bomb dropped on Hiroshima released approximately 63 terajoules, so accelerating a single kilogram to 1/10 the speed of light requires the equivalent of about 7 Hiroshima-scale nuclear events for a single kilogram. Now scale up. A minimal crewed spacecraft, not a luxury vessel, not a colony ship, just a basic life support capsule adequate to sustain a small crew for a multi-year journey, might conservatively weigh around 100,000 kilograms, that is 100 metric tons, which is actually an extremely optimistic lower bound for anything capable of keeping humans alive for years. Accelerating that 100-ton spacecraft to 10% the speed of light would require roughly 45 exajoules of energy. The entire global energy consumption of human civilization in 2023 was approximately 600 exajoules, so this minimal ship, traveling at 1/10 the speed of light, would require energy approximately equivalent to about 7.5% of everything humanity produces and uses in an entire year, and that is just for the acceleration phase, not counting deceleration at the destination, not counting life support for the journey, not counting communications, not counting any margin for error, and at 10% the speed of light, the trip to Proxima Centauri still takes over 40 years. Push the speed to 90% of the speed of light, which would get you to Proxima in roughly 5 years, and the energy requirements become genuinely incomprehensible. The relativistic gamma factor at 90% the speed of light is approximately 2.3, meaning the energy required is 2.3 times what a naive Newtonian calculation would suggest. For our 100-ton spacecraft, we are talking about energy outputs that are orders of magnitude beyond what humanity currently produces in a year. At 99% the speed of light, the gamma factor is over 7. At 99.9%, it is over 22. The energy requirements scale with the Lorentz factor, which grows without bound as you approach light speed, and the energy to reach 90% or 99% the speed of light with any payload of meaningful mass is not merely large. It exceeds the total annual output of all the stars in our galaxy many times over for anything but the most trivially small objects. Antimatter is often invoked here as a solution, and it deserves careful consideration before explaining why it still falls short. When matter and antimatter annihilate, they convert entirely to energy, gamma-ray photons, following Einstein's Ebner-Seidel with 100% conversion efficiency. This is not a technological limit or an engineering constraint. It is the theoretical maximum energy you can extract from mass in the known physics of the universe. There is no more efficient reaction conceivable. A matter-antimatter drive would be, in principle, the ultimate rocket, and yet it is still not adequate for two fundamental reasons. The first is the rocket equation, the Tsiolkovsky rocket equation, formulated in 1897, before relativistic physics even existed, states a mathematical relationship between a rocket's initial mass, its final mass, and the velocity change it can achieve based on the exhaust velocity of its propellant. In its relativistic generalization, the relationship remains merciless. To achieve higher and higher fractions of the speed of light, the ratio of your initial mass to your final mass must grow exponentially. If you want to accelerate a 1-ton payload to 90% the speed of light, and then decelerate at your destination, a round trip requires 4 such burns. The mass of propellant you need dwarfs the payload by factors of tens of thousands. The spacecraft would be almost entirely fuel, and that fuel has to be carried from the start, which means it adds to the mass that needs to be accelerated, which requires more fuel, in an exponential cascade that rapidly becomes self-defeating. This is the same rocket equation that makes reaching Earth orbit expensive despite chemical fuels being readily available. It is just extrapolated to a regime where the numbers reach truly absurd magnitudes. The second problem with antimatter is that we produce almost none of it. CERN's Large Hadron Collider and related facilities produce antiprotons at a rate measured in nanograms per year. The cost of antimatter has been estimated at roughly $62 trillion per gram. The total amount of antimatter produced by all of human civilization's particle physics programs combined, all of it, would, if annihilated, release less energy than a small firecracker. To supply even a small interstellar probe with useful amounts of antimatter propellant, we are talking about kilograms, or more likely tons. We would need to scale up antimatter production by many orders of magnitude and sustain that production, and find safe ways to store antimatter in bulk without it contacting matter and annihilating prematurely. There is no theoretical reason antimatter storage is impossible, but the infrastructure required is so far beyond anything we have built that it represents not a technological gap, but a civilizational transformation, a species that has reorganized its entire economy and energy production around antimatter manufacturing for a period of many centuries, just to fuel one interstellar mission. Suppose, for the sake of argument, we solved all of that. Suppose we had the energy, the propellant, the technology, and the ship. We would then encounter a class of problems that physics imposes on any object moving at a substantial fraction of the speed of light through interstellar space. Problems that are not about the ship or the engine, but about the medium itself. The space between stars is not truly empty. Interstellar space contains what is called the interstellar medium, a diffuse mixture of gas and dust pervading the galaxy. The dominant component is hydrogen, at an average density of roughly 1 atom per cubic centimeter. In some regions, particularly in cold, dense molecular clouds where new stars form, the density can be thousands of times higher. In other regions it can be much lower, but the canonical average of 1 hydrogen atom per cubic centimeter is good enough to illustrate the problem. This sounds sparse, and by everyday standards it is. The best vacuum we can create in laboratories on Earth is far denser, but at the velocities required for interstellar travel, this near vacuum becomes a wall. Consider a spacecraft traveling at 90% the speed of light. From the spacecraft's reference frame, every hydrogen atom in its path is approaching it at 90% the speed of light. The kinetic energy of each individual hydrogen proton at that velocity is approximately 1.1 JeV, about the energy released in a radioactive decay. A cubic meter of interstellar medium at average density contains roughly 1 million hydrogen atoms per second. A spacecraft 1 meter square at 90% the speed of light sweeps through a column of space about 270,000 kilometers long, encountering roughly 270 billion hydrogen atoms. Each of these is a tiny ionizing radiation impact, depositing energy into the forward surface and the ship's structure. The cumulative radiation dose to the ship and its occupants is comparable in intensity to being immersed in the radiation environment of the interior of a nuclear reactor. Not briefly, continuously, for years. Every hydrogen atom impact produces secondary particles, electrons, positrons, pions, that penetrate shielding materials and irradiate everything they reach. A human crew would absorb lethal radiation doses within hours or days, but even for a robotic probe, the material damage accumulates. The forward surface of the spacecraft is continuously being bombarded by subatomic particle impacts at relativistic energies. Every material we know of has a limit to the energy it can absorb before its atomic structure is disrupted. We call this radiation damage, and it is the same phenomenon that limits the lifetimes of materials in nuclear reactors and spacecraft in high radiation environments. At 90% the speed of light for years, the cumulative damage to any material surface would be catastrophic. Dust compounds the problem further. The interstellar medium also contains microscopic grains of solid material, silicate and carbon particles left over from stellar evolution, ranging from tens of nanometers to perhaps a micrometer in diameter, with occasional larger grains. At 90% the speed of light, a single dust grain with a mass of 10-13 grams carries a kinetic energy of approximately 100 gigajoules, equivalent to the detonation of about 25 tons of TNT, not a nuclear weapon. 25 tons of conventional explosive, concentrated at a point smaller than a bacterium, striking your spacecraft at a closing speed of 270,000 kilometers per second. At that energy, the grain does not bounce off, it does not leave a dent. It creates a small nuclear-scale explosion at the point of impact, vaporizing both itself and a significant volume of surrounding spacecraft material, sending a shockwave through the structure and producing a burst of secondary radiation. The density of large dust grains in interstellar space is much lower than hydrogen atoms, but across 40 trillion kilometers of travel, you will encounter many of them. Each encounter is an explosion. There is no material known to science, and no material whose existence is suggested by our understanding of condensed matter physics that could survive sustained bombardment by these events. There is also the radiation problem from another angle entirely. At relativistic velocities, the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space uniformly at a temperature of about 2.7 Kelvin, is dramatically blue-shifted from the spacecraft's forward perspective. At 9% the speed of light, the CMB photons arriving from the forward direction are blue-shifted by the Doppler factor of the Lorentz transformation from microwave frequencies all the way up into X-ray territory. The spacecraft's forward hemisphere would be bathed in a continuous flux of energetic X-radiation, coming not from any star but from the universe itself, from the cosmic background that permeates every cubic centimeter of space. This radiation would penetrate any conventional shielding and irradiate the spacecraft's interior continuously throughout the journey. At 99% the speed of light and above, the CMB blue shifts into gamma ray territory, and the energy density experienced by the ship would be lethal to biological systems within seconds. Together, hydrogen impacts, dust grain detonations, CMB blueshift radiation, and secondary particle cascades create an environment at relativistic speeds that no material science currently understood, and no material science plausibly reachable through extensions of current understanding can protect against for the duration required. The engineering community has looked at some of these problems seriously in the context of Breakthrough Starshot, a proposed mission to send gram-scale laser-propelled sails to Alpha Centauri at 20% the speed of light, a velocity well below the most extreme scenarios I have described. Even at 20% the speed of light, the radiation and particle impact environment is a primary unsolved challenge, and the candidate materials being considered are experimental, fragile, and uncertain. At 90% the speed of light, the problem is not harder. It is a different category of problem entirely. Navigation and control add another layer of impossibility that is frequently underappreciated. We are accustomed to thinking of spacecraft navigation as a solved problem. We routinely steer probes to within kilometers of their intended targets after journeys of years and billions of kilometers. The precision of our navigation for missions like New Horizons and Cassini is genuinely extraordinary, but all of that navigation is performed at speeds that are tiny fractions of the speed of light. At relativistic speeds, the physics of navigation changes in ways that remove our familiar tools. The fundamental problem is that information travels at the speed of light. To detect an obstacle, a sensor must receive light or other radiation that has bounced off the obstacle and returned to the spacecraft. For an object directly ahead, the closing speed is effectively the spacecraft's own velocity. At 90% the speed of light, the time between when reflected light from an obstacle enters the forward sensor and when the spacecraft reaches the obstacle's position is determined by the geometry, and for any obstacle detected at a reasonable range, that time is measured in milliseconds or microseconds. No mechanical system and no electronic system subject to the finite propagation speeds of electrical signals within circuits can detect, process, evaluate, and execute a course change in time to avoid an obstacle detected at typical interstellar particle densities. The universe enforces this not through engineering difficulty, but through the speed at which information itself can travel. Relativistic aberration compounds the navigational problem. At high velocities, the apparent positions of stars and other objects in the sky are distorted by the motion of the observer. A spacecraft traveling at 90% the speed of light sees the entire forward sky compressed into a bright, distorted oval. Stars that would normally be visible across the full forward hemisphere are bunched together toward the direction of travel due to the aberration of light. Meanwhile, the backward sky stretches and dims. The starfield the navigator would use for reference is not the starfield they expect. The wavelengths of light from stars ahead are blue shifted. Stars that are normally yellow or orange appear blue or even ultraviolet. Stars behind are red shifted into dim orange and infrared. The entire visual experience of space at relativistic velocities is alien, distorted, and deeply counterintuitive. And critically, the Doppler shift of electromagnetic signals from Earth, which would be your primary communication and navigation reference, becomes so severe that communication requires careful compensation for the shifting frequencies, adding complexity to every signal exchange and requiring that the ship's systems know their own velocity with extraordinary precision. The reaction time problem is perhaps the starkest. At 90% the speed of light, the spacecraft covers 270,000 kilometers in 1 second. A hydrogen atom in its path provides no radar return. It is a single proton, invisible to any sensor we could conceivably mount on a spacecraft. A dust grain might scatter some radar energy, but the time between detection and impact, even for something detectable at a kilometer's range, is approximately 3.7 microseconds. At that timescale, even light traveling within the spacecraft's control circuits, from sensor to processor to actuator, might not complete the circuit in time for any useful maneuvering response. This is not an engineering problem that faster computers will solve. It is the universe imposing the finite speed of signal propagation as an absolute constraint on reaction times. At at scales where the closing velocities are comparable to the speed of light itself. Let us now step back from the spacecraft entirely and look at the larger gravitational architecture that surrounds us, because there are structural constraints that operate at the galactic scale and beyond. Our solar system exists within the Milky Way galaxy, a barred spiral disk of roughly 200 to 400 billion stars, approximately 100,000 light years in diameter, embedded in an extended halo of dark matter that reaches far beyond the visible disk. The total mass of the Milky Way, including its dark matter halo, is estimated at somewhere between 750 billion and 2 trillion solar masses. The gravitational field produced by this mass is what keeps stars in their orbits and holds the galaxy together. To escape the Milky Way entirely, to travel into the intergalactic void, an object must achieve the local escape velocity, which at our position approximately 26,000 light years from the galactic center is approximately 550 kilometers per second. Compare this to other escape velocities you may be familiar with. Earth's escape velocity is about 11 kilometers per second. The Moon's is 2.4 kilometers per second. The Sun's escape velocity at Earth's orbital distance is about 42 kilometers per second. To escape the Milky Way from our location requires moving at 550 kilometers per second, about 13 times the velocity needed to escape from the Sun's pull at our current position, and roughly 50 times Earth's escape velocity. Voyager 1, moving at 17 kilometers per second, is heading out of the solar system, but would need to be traveling more than 32 times faster to escape the galaxy. It will not escape the galaxy. It will spend billions of years orbiting the galactic center as part of the Milky Way, in the same way Earth orbits the Sun, gravitationally bound, regardless of its local motion through the interstellar medium. The dark matter halo of the Milky Way extends to perhaps 200,000 to 300,000 light years in radius, 2 to 3 times the diameter of the visible disk. This halo of invisible matter, detectable only through its gravitational influence on stars and gas, provides the dominant gravitational pull that governs the galaxy's structure. Without it, the outer stars of the Milky Way would fly apart. The visible matter alone does not provide enough gravity to explain the observed rotation curve of the galaxy. Dark matter's existence is inferred, not directly detected, but the inference is so robust, supported by galaxy rotation curves, gravitational lensing, the large-scale structure of the universe, and the cosmic microwave background power spectrum, that serious alternative explanations have been largely ruled out, and one of its effects is to make the Milky Way's gravitational well deeper and more extended than the visible stars alone would create, making escape from it even harder than a naive count of stellar masses would suggest. Now let us turn to what is perhaps the most philosophically striking physical constraint of all, not the distances between stars within our galaxy, not the speed of light, not the energy requirements of relativistic travel, but the expansion of the universe itself. Because while Proxima Centauri is gravitationally bound to us and is not receding, the vast majority of the observable universe is. And understanding why matters enormously for how we think about the cosmos. Edwin Hubble, working at the Mount Wilson Observatory in the 1920s, established through careful observation of the spectra of distant galaxies that they were moving away from us. More importantly, he established that the farther a galaxy was, the faster it was receding, a linear relationship now called the Hubble law. The modern understanding of this observation is not that galaxies are moving through space away from us as debris from an explosion, but that the fabric of space itself is expanding, stretching out new volume everywhere, carrying distant galaxies apart from one another as a raisin bread swells, and the raisins separate, not because the raisins are moving through the bread, but because the bread itself is growing. The current best measurement of the Hubble constant is approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance between us and a galaxy, that galaxy is receding from us at an additional 70 kilometers per second due to cosmic expansion alone. For nearby galaxies, Andromeda at 2.5 million light years, this cosmological recession is swamped by the gravitational attraction between us, and Andromeda is actually approaching us. The local group of galaxies, of which we and Andromeda are the two dominant members, is gravitationally bound, expansion is irrelevant within it. But beyond the local group, at distances of tens and hundreds of millions of light years, the recession velocities become significant. At distances of several billion light years, galaxies are receding at substantial fractions of the speed of light, and at a distance of approximately 4.4 billion light years, the Hubble radius, galaxies are receding from us at exactly the speed of light. Beyond that distance, something striking happens. Galaxies are receding from us faster than light. This is not a violation of special relativity. Those galaxies are not moving through space faster than light. Space itself is expanding, carrying them along, and the rate of expansion of the intervening space exceeds light speed. Any light emitted by such a galaxy, heading toward us, faces a headwind. The space it must traverse is expanding faster than it can travel through it. The light loses ground. It will never reach us. Those galaxies are, right now, beyond our ability to ever observe or communicate with, not because they are hidden behind anything, but because the universe is expanding too fast. The boundary within which objects can still send us light, the cosmic event horizon, currently sits at approximately 16 billion light years from Earth. This is a meaningfully different thing from the observable universe, which extends to about 46 billion light years in all directions and contains objects whose light has had 13.8 billion years to reach us. The observable universe is large because the universe was smaller when light from distant objects was emitted, and those photons have been traveling through expanding space ever since. But the event horizon is the boundary beyond which any light emitted today will never reach us, because the expansion of space will carry it away faster than it can travel toward us. Dark energy, the mysterious component of the universe's energy budget that appears to be causing the expansion to accelerate, makes this horizon permanent and counterintuitively shrinking in terms of accessible objects. In the 1990s, observations of Type A supernova by two independent teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, work that earned the Nobel Prize in Physics in 2011, established that the expansion of the universe is not slowing down due to gravity as cosmologists had assumed. It is speeding up. Something is pushing space apart at an accelerating rate. We call it dark energy because we do not know what it is, only that it constitutes approximately 68% of the total energy budget of the universe and exerts what amounts to a repulsive pressure on space-time at large scales. The cosmological constant in Einstein's field equations, a term he initially added and then famously retracted, calling it his greatest blunder, turns out to be the best mathematical description of dark energy we have, though its physical interpretation remains deeply uncertain. The consequence of accelerating expansion is that as time goes on, more and more galaxies cross our event horizon and cease to be reachable, even in principle. The galaxies we can currently see in the far universe are sending us their last messages, light that will take billions of years to arrive, trailing off as the source recedes beyond the event horizon. For galaxies beyond the local group, the moment has already passed. Their future light is already falling behind, already losing the race against the expanding void. On the grandest cosmological timescales, this has a consequence that should give us genuine pause. In approximately 100 to 150 billion years, when the universe is roughly 10 times its current age, almost all galaxies currently visible to us will have been carried beyond our event horizon. The tens of thousands of galaxies we currently observe in a single Hubble Deep Field image will be gone from the sky, not destroyed but simply carried beyond reachability. Future observers on what remains of Earth, or whatever has evolved and survived by then, will see a sky populated only by the stars and galaxies of the local group, our own Milky Way, Andromeda, the Magellanic Clouds, and a few dozen smaller satellite galaxies and dwarf galaxies. Beyond that, darkness, a universe that appears, to those future observers, to contain only a single galaxy cluster surrounded by an empty void. The cosmic microwave background will have redshifted to wavelengths so long that it is undetectable without instruments of science fiction capability. The large-scale structure of the universe, the great web of filaments and voids and clusters that we use today to understand the universe's history, will be invisible. Those future astronomers, however advanced, will have far less information available to them than we do today, If they manage to develop physics and cosmology, they may correctly suspect that the universe is larger than what they can see, but they will have no observational evidence, no CMB, no distant galaxy redshifts, no large-scale structure surveys. They will be cosmologically blind in a way we are not. The rich picture of the cosmos we have assembled over the last century, the history of the universe from its first fraction of a second to the present, is a picture available only in this cosmological era, when the universe is old enough for intelligent life to have evolved, but young enough for the evidence of its origins and extent to still be accessible. We live in the single window of cosmic history during which the universe is fully observable by minds capable of observing it. That window is cosmologically brief, and it is already, in the longest view, beginning to close. This means that if there is to be any understanding of the universe's true scale and history, if any mind anywhere is to know what we know about the cosmos, it must happen now, in this era, within this few billion-year window. And we happen to be here in this window capable of looking. This is not comfort, exactly. It is something stranger and more precise than comfort. It is the recognition that we arrived at the right moment to see everything, and that we cannot travel to any of it. Let us now be thorough about what this all means practically, about what is truly impossible, what is merely extremely difficult, and where the honest boundary between the two lies. This is important because intellectual honesty requires distinguishing between things that physics forbids and things that engineering has not yet achieved. There is a category of interstellar concepts that are not forbidden by physics, only by engineering at scales so vast that they represent essentially civilizational level undertakings across centuries or millennia. Generation ships, spacecraft large and self-sufficient enough to sustain a multi-generational human population for the tens of thousands of years required to cross interstellar distances at achievable velocities, are constrained not by any physical law but by ecology, genetics, social organization, and engineering at scales far beyond current capability. A viable generation ship would require closed-loop life support systems of extraordinary reliability. Air, water, food, waste processing, working perfectly for 10,000 years with no resupply, no external maintenance, and no possibility of a hardware store. It would need to maintain sufficient genetic diversity, likely requiring hundreds or thousands of founding individuals, or sophisticated genetic preservation and reproductive technology to avoid the catastrophic inbreeding that would otherwise accumulate within a small isolated population over dozens of generations. It would need stable social institutions across time periods longer than any human society has ever maintained its coherence. It would need propulsion adequate to maintain a manageable journey duration without requiring energies that violate the considerations we have already discussed. None of these is physically impossible, but the combined requirements represent a project so demanding that it would dwarf every engineering achievement in human history by multiple orders of magnitude, and it would do so for a journey whose beneficiaries are not the people who build it or launch it, but people born and raised entirely in space, who have never seen Earth, arriving at a destination neither they nor any ancestor alive at launch has ever seen. Suspended animation, the idea of putting crew into a state of dramatically reduced metabolism to sleep through the bulk of the journey, is a concept with genuine biological precedent. Certain organisms achieve states of suspended metabolic activity. Tardigrades can survive extreme desiccation. Some fish and reptiles survive extended winter dormancy. But human cells are not designed for this, and the biological machinery required to preserve the full complexity of a human nervous system through thousands of years, preventing molecular damage, DNA degradation, membrane deterioration, and the accumulation of the thousand subtle injuries that biochemistry suffers even in the absence of active metabolism, is a problem whose solution is not clearly suggested by any current line of research. Whether it is achievable in principle is genuinely unknown. The honest answer is that we do not know if a human can be preserved for even 1,000 years, let alone 70,000, and even a hypothetically perfect suspended animation technology does nothing to address the energy problem, the shielding problem, or the navigation problem. There is also the concept of mind uploading, the transfer of a human consciousness, or something sufficiently like it, into a computational substrate that could be transmitted at or near the speed of light, then instantiated at the destination. This idea rests on a cascade of assumptions, each uncertain, that consciousness is substrate, independent, philosophically contested, that a digital representation of a mind is the same mind rather than a copy debated, that we could capture sufficient detail of a human brain's connectivity to recreate it is technologically nowhere near achievable, and perhaps fundamentally limited by quantum uncertainty, and that something could be instantiated at the destination without a pre-existing receiver. Each of these assumptions represents not an engineering gap, but a philosophical and scientific question without agreed upon answers. Mind uploading as a mode of interstellar travel is not possible but difficult. It is possible only if several things we don't know turn out to be true in the ways we hope. What we can say with genuine confidence, grounded in confirmed physics and honest engineering assessment, is this: with the science we understand, with any technology extrapolable from what we currently know, and with any realistic projection of progress over the next several centuries, crude interstellar travel is effectively impossible. Not difficult, not expensive, effectively impossible. For robotic probes, the picture is marginally less bleak. A sufficiently small probe, driven by a sufficiently powerful laser array, could potentially be accelerated to meaningful fractions of the speed of light without carrying its own propellant, bypassing the rocket equation. The breakthrough Starshot proposal genuinely engages with this possibility, but even there, the shielding problem, the communication problem, and the question of what exactly a gram-scale chip can do when it arrives are all unsolved, and the journey time at 20% the speed of light is still over 20 years. A gram-scale chip arriving at Proxima Centauri after a 20-year flight cannot establish a colony, cannot bring back samples, cannot do anything that transforms our relationship with interstellar space in a fundamental way. It can take pictures and transmit them. That is remarkable. It is not interstellar travel in any sense that changes the human condition. There is a psychological dimension to all of this that deserves honest attention, because the emotional response to these conclusions matters for how we relate to the cosmos. Human beings are explorers, not metaphorically, but in the most literal evolutionary sense. The archaeological record tells us that Homo sapiens crossed open ocean from Southeast Asia to Australia at least 65,000 years ago, without metal tools, powered boats, or written navigation charts. Our species walked across land bridges and ice sheets to inhabit every continent on Earth. We were in the Americas, fully adapted to high-altitude environments in the Andes and to desert conditions in the Atacama, thousands of years before European civilizations had seafaring ships. When Polynesian navigators crossed the Pacific, the largest single expanse of open water on the surface of the Earth, they did so by reading stars, ocean swells, bird behavior, cloud patterns, and the subtle color and temperature variations of the water itself, with a precision that modern oceanographers still study with genuine admiration. The drive to move, to cross what has not been crossed, to see what lies beyond the visible horizon. This appears to be something genuinely fundamental to our nature, selected for over hundreds of thousands of years because it worked. It allowed our species to find new resources, escape failing environments, and persist in conditions that would have eliminated species with smaller ranges. We reached the moon. 12 human beings walked on another world, and they did so within living memory, and they came back to tell us what it was like. 4 people who walked on the moon survived to see the year 2000. It happened. It was real, and Mars is a realistic target within the next generation. Not easy, not cheap, not without dangers that will likely kill people, but achievable without any new physics, achievable with extensions of technology we already have. The solar system, all of it, from the sun to the heliopause and the inner Oort cloud, across a span of roughly 1 or 2 light years, is, in principle, accessible, not cheaply, not quickly by human standards, but traversable without violating any physical law. With centuries of sustained effort and technological development, we could become a species distributed across multiple worlds and habitats within our solar system. There is enormous and genuinely profound exploration available within our own gravitational backyard, the moons of Jupiter and Saturn, Europa, Ganymede, Enceladus, Titan, may harbor subsurface liquid oceans and perhaps even microbial life. The asteroid belt contains resources of staggering quantity. The outer solar system is a vast and barely explored territory whose full character we have only begun to understand. Humanity's destiny as an exploratory species is not foreclosed. It is simply local. The stars are another matter, and understanding why requires confronting something that most science communication is reluctant to state plainly. The universe does not owe us accessibility. The same physical laws that make matter stable, that allow hydrogen to fuse into helium in the hearts of stars and release the energy that warms planets, that permitted the chemistry of life to assemble itself on this warm, wet world over 4 billion years. Those same laws, in their completeness and their impartiality, also impose absolute limits on where we can go. The universe is not withholding interstellar space from us the way a border guard withholds passage. The universe has structured space-time in such a way that the distances between stars are not merely large, but large in a way that is specifically and irreducibly resistant to traversal by anything with mass. The only thing that crosses interstellar distances in any reasonable time is light, which carries no mass, faces none of the escalating energy requirements, and obeys none of the rocket equation's tyrannies. We can see the universe. We can understand it with remarkable precision. We simply cannot go there. This could be framed as a prison, but that is the wrong analogy. A prison is built by someone to hold someone against their will. The structure of space-time has no architect and no intent. It is simply what the universe is. Every civilization in this galaxy, if others exist, faces exactly the same arithmetic. Every species of intelligence that has ever evolved, anywhere in the observable universe, operating under the same physics we know earlier, and we have every reason to believe physics is universal, since the spectral lines of distant stars are identical to those in our laboratories, has looked up at the stars and confronted the same distances, the same speed limit, the same energy requirements. The gaps between stars are not a punishment. They are the geometry of the universe as it emerged from the Big Bang, shaped by the interplay of gravity, quantum mechanics, and thermodynamics over 13.8 billion years. They are what they are. The distances between stars are a consequence of how matter collapses under gravity to form stars, how those stars distribute themselves within the gravitational potential of the galaxy, and how the interstellar medium, the gas and dust from which new stars form, distributes itself across galactic scales. Stars do not cluster more tightly because a more tightly clustered distribution would not be stable. The gravitational dynamics of many massive objects in very close proximity lead to chaotic three-body interactions, ejections, binary mergers, and disruptions on timescales short by astronomical standards. The average spacing of stars in our neighborhood of the galaxy, several light years between neighbors, is the natural outcome of this gravitational dynamics playing out over billions of years. It is the same physics that governs the orbits of planets around our sun, the same gravity that holds us on the surface of this planet. We cannot be angry at it. It is what physics does. There is a particular kind of wonder that comes from understanding this clearly, not the false wonder of speculative loopholes or the warm, but imprecise wonder of one day we'll get there. But the cold, precise, somewhat vertiginous wonder of comprehending the actual scale and structure of the cosmos without any softening. We know the distance to Proxima Centauri to 4 significant figures. We know the speed of light to 9 significant figures. We know the relativistic energy equations with sufficient precision to design particle accelerators that work to within millionths of a percent of their design specifications. We know the density of the interstellar medium from radio telescope observations of hydrogen's 21 centimeter spectral line, mapped across large portions of the galaxy. We know the Hubble constant from multiple independent measurement methods that agree to within a few percent. And the disagreement between those methods, known as the Hubble tension, is itself one of the most actively studied puzzles in modern cosmology. We know the size of the cosmic event horizon from our models of dark energy and cosmic expansion, models that are confirmed by dozens of independent lines of observational evidence. All of this knowledge was assembled by human minds working within the constraints of a single small planet, using instruments that are microscopic on astronomical scales, over a period of time that is a blink in cosmic terms. That we know these things at all is an extraordinary fact about the universe. That it is knowable, that its structure can be inferred from inside it by examining the light that passes through it, that mathematics developed for entirely abstract reasons turns out to describe physical reality with astonishing precision. The universe is approximately 13.8 billion years old. Earth formed about 4.5 billion years ago. Liquid water existed on Earth's surface within a few 100 million years of formation. Life appeared in some form within roughly a billion years. Complex, multicellular life, animals, plants, fungi, organisms with differentiated tissues and specialized organs, required another 3 billion years. Homo sapiens has existed for at most 300,000 years. Written civilization, the ability to record and transmit knowledge across generations in symbolic form, is perhaps 6,000 years old. The heliocentric model of the solar system is roughly 500 years old. The understanding that other stars are suns, possibly with planets, is perhaps 400 years old. The measurement of stellar distances by parallax is about 180 years old. The scientific understanding that let us compute the distance to Proxima Centauri, the speed of light, and the relativistic energy equations required to assess the feasibility of interstellar travel is, at most 120 years old. In the full arc of cosmic time, we are so new that the word newborn flatters us, and in that implausibly brief existence, we have worked out why we can never go there. We have done the mathematics of our own confinement. We have sat with that knowledge, and we have continued to look up anyway. That is worth dwelling on for a moment. We looked at the stars and we calculated the distance. We measured the speed of light in a laboratory and understood that it was a universal constant. We derived the equations of relativity and we tested them until we were certain. We measured the interstellar medium with radio telescopes and calculated what it does to a vehicle moving through it at high speed. We computed the energy requirements and compared them to everything we produce. We traced the implications of dark energy and worked out when galaxies will pass beyond our event horizon forever. We did all of this knowing it would not make the stars any closer. We did it purely to understand, and we are the first minds we know of in 13.8 billion years of a universe that has been doing all of this without witnesses, who have made even a partial accounting of what is out there and why it is unreachable. There is a concept sometimes called the cosmic perspective, the view of ourselves from outside, as a small species on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. Carl Sagan articulated it with characteristic power. Neil deGrasse Tyson has given it a modern voice. But the version of the cosmic perspective that emerges from taking the physics seriously, from following the numbers wherever they lead, is simultaneously more humbling and more strange than the popular version. We are not merely small, we are also, in a physically precise sense, isolated. Not small and surrounded by a vast universe we might one day explore and populate. Small, isolated, pinned by physics to a single star, watching a universe we understand with remarkable precision and can visit only with our eyes and our mathematics. And yet, the nearest star is 4.24 light years away, and we know that. We know what kind of star it is. A red dwarf, spectral class M55V, with approximately 20% of the Sun's mass, about 14% of the Sun's radius, and 0.1% of the Sun's luminosity. We know it has at least one planet, Proxima Centauri b, orbiting in the habitable zone at a distance of about 0.05 astronomical units with a period of 11.2 Earth days. We know that Proxima is gravitationally bound to the Alpha Centauri system, the binary pair of Alpha Centauri A and B, lying about 0.2 light years further from us, and that together they form a triple star system at 4.4 to 437 light years distance. We know all of this without ever having gone there, without any probe within a light year of the destination, from the comfort of this planet, using spectroscopy and radial velocity measurements and transit photometry. We know the stars intimately, we just cannot touch them. In the night sky, on a dark night far from city lights, you can see roughly 9,000 stars with the naked eye, all of them within a few thousand light years of Earth, all of them within our own corner of the Milky Way. Every one of those points of light is a sun. Many have planets. Some of those planets may be warm and wet and alive with something that can look back across across the same void and do the same mathematics and reach the same conclusion? We will never know, not because we have not tried, but because the universe ensures that we cannot know, that the signals crossing interstellar distances carry only light, speed information, that any response to our transmissions takes years to decades to receive, and that any physical exchange of matter between star systems is subject to all of the barriers we have spent this document examining in detail, that we find this beautiful, that the honest confrontation with cosmic isolation produces not despair but a particular kind of clear-eyed awe, says something about the kind of minds we are. We are the universe's way of knowing itself, as a number of people have said in various formulations, and that remains true even in confinement. Even pinned to one star, even unable to cross the dark between stars. The knowing is real, the understanding is genuine, the mathematics is correct, and the star is there, 4.24 light years away, quietly burning, indifferent, magnificent, and we know exactly where it is and why we cannot go there, and we stare at it anyway with everything we have, which is all any mind in any universe can do. This is the defining fact of our cosmic position. We are local, not by walls or hostility or accident, but by the structure of space and time, by the speed of light and the equations of relativity and the density of the interstellar medium and the acceleration of cosmic expansion. The nearest star is 4.24 light years away, and the best thing we have ever built would take 73,000 years to get there. The physics of mass and energy makes meaningful acceleration effectively impossible within known science. The interstellar medium would destroy any vehicle moving fast enough to matter. The universe beyond our local group is actively and permanently receding beyond our event horizon, and the cosmological timeline tells us that even the era in which we can see all of this, the era of a fully visible, fully measurable, cosmologically legible universe, is itself cosmologically brief, a narrow window in which understanding is possible before the darkness closes in from all sides. There is a Russian concept, or perhaps it is a universal human feeling that a particular word merely captures more precisely than most, called toskata, deep, aching, wistful longing for something you cannot have and perhaps cannot fully name. It is not grief. It is not depression. It is closer to the feeling of standing at a shoreline at dusk, looking at the horizon, knowing that beyond it lies something real and beautiful and permanently out of reach, and feeling that fact in your chest in a way that is not quite pain and not quite wonder, but something of both. The universe, looked at clearly, inspires something like this. We are here, on this small warm planet, capable of building instruments that detect gravitational waves from black hole mergers a billion light years away, capable of imaging the shadow of a supermassive black hole, capable of sequencing the genomes of organisms and modeling the first microseconds after the Big Bang. And that same capability reveals, with perfect clarity, that we are not going anywhere. Not to Proxima Centauri, not to Alpha Centauri, not to any of the billions of star systems we can map in the Milky Way. We are here. This is where we live. This is the domain allocated to us by the physics of the universe: one star, one solar system, 8 planets and their moons and rings, a belt of asteroids, a vast cloud of comets, a neighborhood of extraordinary richness and complexity that we have barely begun to explore. And beyond that, darkness full of stars we can see and study and understand and never reach. The view we have of that darkness is not permanent. The cosmic event horizon is contracting in terms of accessible objects. The distant galaxies are retreating. In a billion years, the sun will be meaningfully hotter, and Earth's long-term habitability becomes uncertain. In 5 billion years, the sun will expand into a red giant, and this planet will be gone. The local group will merge into a single irregular mass over the next few billion years. The stars of the combined galaxy will slowly exhaust their fuel and fade over tens of trillions of years, leaving cold remnants in an increasingly dark and cold universe. Everything we have built, everything we have understood, everything we have been, all of it is temporary. But it is here now. We are here now. We have the view now. The nearest star is 4.24 light years away, and we know exactly how it burns and how old it is and what orbits it and why we can never go there. And we look at it in the clear night sky with naked eyes that evolved for an entirely different purpose, and we feel the distance and we keep looking. That is not nothing. In a universe 13.8 billion years old, containing more stars than there are grains of sand on all of Earth's beaches, in which no physical law requires the existence of minds capable of contemplation at all, the fact that we exist and that we understand is extraordinary. The fact that the universe is comprehensible, that the same mathematics describes both the curve of a thrown stone and the orbit of a galaxy, that the same atomic physics underlies both the chemistry of life and the fusion of stars, that space and time are woven into a single fabric whose geometry we can map with instruments we built with our hands. This is not something the universe owed us. It is something we discovered, carefully, painfully slowly, against the resistance of our own cognitive limitations and the difficulty of the observations. And what we discovered is real. The nearest star is real. The distance is real. The barriers are real. And so is the understanding. That view will not last forever. But we have it now. We have it now in a way that no future civilization may have it, because the cosmic event horizon is slowly closing and the distant galaxies are receding past it one by one. We have it now in a way that makes this precise moment in cosmic history, this brief, fleeting moment when a species of primate on a rocky planet around an ordinary star in the outer arm of a spiral galaxy has looked up and understood the universe, uniquely and permanently significant. The universe will be older and darker and quieter in 1 trillion years. The knowledge we have assembled may be lost, or it may be preserved in forms we cannot imagine, or it may be rediscovered by minds we cannot conceive of. But the moment of first understanding, the moment when the distance to the nearest star was measured, the speed of light was constrained, the equations of relativity were written and tested, the event horizon was calculated and understood, that moment is this one. We are in it, and so we watch, and we measure, and we calculate, and we look at Proxima Centauri in the southern sky, our nearest neighbor at 4.24 light years, burning quietly and steadily in the dark, unreachable, beautiful, real. And we know, with as much precision and honesty as our science allows, exactly why we cannot go there, and exactly what it means that we know that. And we keep looking anyway, because the universe is there, and we are here, and understanding is what we do. Consider what has been assembled across this document, not as a catalogue of limits, but as a map. The distance to Proxima Centauri is 40.1 trillion kilometers, a number arrived at through the parallax method, measuring how much a nearby star appears to shift against the backdrop of far more distant stars as Earth orbits the Sun. The angle is tiny, less than 1 arcsecond, equivalent to the width of a dime seen from a distance of 2 kilometers, but we measure it with precision, and from it we derive distance. The speed of light was first meaningfully constrained by All Armour in 1676. By observing variations in the timing of Jupiter's moon Io, he noticed the eclipses ran early or late depending on whether Earth was moving toward or away from Jupiter, and correctly attributed this to the finite speed of light. Modern measurements, using laser pulses bounced off retroflectors left on the moon, give us a value accurate to better than 1 meter per second. The equations of special relativity were confirmed by every precision test ever devised for them. The behavior of particles in accelerators, the lifetimes of muons at relativistic speeds, the precise timing of GPS satellites, the energy output of nuclear reactions, the Lorentz factor, the mathematical expression at the heart of the relativistic mass increase and time dilation has been tested to extraordinary precision and has never failed. It is not an approximation. It is not a model. It is how the universe works. The density of the interstellar medium was mapped by radio astronomers beginning in the 1950s, when the 21-centimeter emission line of neutral hydrogen was first detected from space. Hydrogen atoms, when the spin of their electrons spontaneously flips, emit a photon at exactly this wavelength, a quiet radio beacon that we can detect from across the galaxy. By mapping the intensity and Doppler shift of this signal in every direction, we have assembled a detailed 3-dimensional picture of how hydrogen is distributed across the Milky Way. The average density of 1 atom per cubic centimeter is not an estimate. It is an observational result. The cosmic microwave background was discovered by accident in 1965 by Arno Penzias and Robert Wilson, who detected a faint, uniform microwave noise coming equally from all directions and could not explain it. until Robert Dickey's group told them they had found the afterglow of the Big Bang. It has since been measured with extraordinary precision by the QOBW-MAPE and Planck satellite missions, and its properties confirm the standard cosmological model to a level of precision that is genuinely remarkable. The Hubble constant, dark energy, the cosmic event horizon, these are derived from a combination of type A supernova distances, galaxy redshifts, CMB anisotropy measurements, and baryon acoustic oscillation surveys. They are not guesses. They are the current best answers of a field that has been rigorously self-testing for over a century. What this means is that the picture presented in this documentary is not pessimism. It is not a failure of imagination. It is the honest summary of what the best science we have ever done tells us about the universe we actually inhabit. There are people who will say that science once said heavier than air flight was impossible, or that we would never leave Earth's atmosphere, or that the 4-minute mile could not be broken. And those examples are real. There have been incorrect predictions, overconfident claims of impossibility, failures of scientific imagination at individual moments. But this is not that. The speed of light being a universal constant is not a prediction. It is an observation confirmed by every experiment ever designed to test it. The relativistic mass increase is not an extrapolation. It is measured directly in particle accelerators, where protons are accelerated to within a fraction of a percent of the speed of light, and their relativistic mass increase is not just confirmed but required for those machines to function. The rocket equation is not a limitation of current technology. It is a consequence of conservation of momentum, which is as fundamental as any law in physics. The barriers to interstellar travel are not walls erected by limited thinking. They are the structure of the universe, and understanding that structure, really understanding it with full mathematical and physical clarity, produces something that feels different from ordinary disappointment. It produces a kind of spacious acceptance. The way understanding why certain mathematical proofs cannot be constructed differently produces not frustration but clarity. The universe is this way. It is knowable, and it is telling us what it is. And what it is includes enormous distances, a speed limit built into the fabric of space-time, escalating energy requirements that diverge to infinity at the speed limit, a medium between stars that becomes lethal at the velocities required, and a cosmic expansion that is actively removing most of the universe from our reach. All of this is real. All of it is, in the deepest sense, the universe being what it is. And within that universe, on this warm, rocky planet with its thin atmosphere and its liquid water and its 4 billion years of continuous biological experiment, something happened that was not inevitable. The emergence of minds capable of working all of this out. Minds that can trace the path of a photon from the surface of a distant star through 4.24 years of travel, into the lens of a telescope, through the optics of a spectrograph, onto a photographic plate or a CCD detector, and from the resulting data infer the temperature, mass, age, chemical composition, radial velocity, and orbital properties of a star we have never approached. Minds that can reason forward from physical first principles to determine that the same star's planets would be bombarded by intense stellar flare radiation, and that any life there would need specific adaptations to survive it. Minds that can calculate the energy required to accelerate to the speed of light and determine that it is infinite, all while sitting on the surface of a planet that has never left its solar system. There is something almost comic about this, if you hold it at a certain angle. The universe made minds, and those minds looked at the universe, and the universe told them they were stuck. The explorers are grounded, the curious are contained. The species that crossed every ocean and every continent and eventually left the planet entirely has hit a wall made of physics that it can see clearly and touch never. We are cognitively capable of imagining every detail of what it might be like to stand on the surface of Proxima Centauri b, the reddish sky, the enormous disk of the nearby red dwarf, the tidally locked day side and night side, the potential auroras cascading across the upper atmosphere during a stellar flare. And we will almost certainly never stand there. Not us, not our children, not the children's children, not anyone who could be called our civilization in any meaningful continuity of culture or memory. That is a strange thing to sit with, and the healthy response, the intellectually honest response, is not to pretend the wall doesn't exist, not to reach for speculative escape hatches that the physics doesn't actually provide, but to sit with the strangeness of it and let it be what it is. The universe is not asking for our approval. It is not organized around our ambitions. It existed for 9.2 billion years before this planet formed, and for 4.5 billion years after that before anything on it could look up and ask questions. The fact that it is now legible to us, that we have, in the last 400 years, assembled enough understanding to map its large-scale structure, measure its age, determine the composition of distant stars, and calculate the barriers to interstellar travel. This is something the universe did not owe us. It happened because the universe turned out to be describable by mathematics, and because evolution produced brains capable of mathematics, and because those brains, over many centuries of effort, developed the tools to apply mathematics to observation. None of that was guaranteed, and it is here now in us, in this conversation, in this precise moment of cosmic history. That is what we are, not the explorers who will cross to the next star, the explorers who understood why we cannot. That is a different kind of achievement, quieter, more austere, without the drama of arrival, without the flag planted and the photograph taken and the journey home to tell the story. But it is genuine, it is true, and the understanding itself, the map of what is out there and why it is unreachable, is a form of contact with the universe that is available to us even from here. We know the nearest star. We know its temperature and its mass and its planets. We know the structure of space-time that separates us from it. We know the laws that govern every particle in the void between here and there. We have, in the only way available to minds pinned to one star in one galaxy, reached out and touched the cosmos with our understanding. And the cosmos, in its vast and indifferent grandeur, has told us everything it knows. The nearest star is 4.24 light years away. We will never reach it, and we know exactly why. If you love deep space deep dives, you can subscribe. It helps more than you think.